like to start by thanking the organizers for the opportunity to speak at this conference and for their great courage also in making it happen at all. So I would like to speak about the results of several recent papers, and the paper from 2016 with Nikolai Gromov, Paul Ryan, Dima Volin, also Andrea Cavaglia, which for some reason Andrea Cavaglia. And so we studied the problem of separation of variables for higher rank integrable spin chains with SUN or SLN symmetry. And in particular, we were able recently to solve the long-standing problem of obtaining the measure for scalar products in separated variables. So the motivation to study this is to develop new methods to compute correlators in various integrable models from spin chains to ADS CFT. And in general, the expectation is that in any integrable model, there should exist a basis in which the wave functions factorize. Like for hydrogen atom, they factorize in spherical coordinates. Here, they would factorize into some building blocks known as Q functions, which for spin chains are polynomials. For ADS CFT, they are more complicated. And this method gives a simple representation for wave functions, so it gives a way to access more complicated off-shell observables like correlators, form factors, and so on. And the method is expected to be very powerful. However, for a long time, it has been almost undeveloped beyond the GL2 case, so beyond rank 1 symmetry. And if we could understand this picture precisely, it would shed light on many open problems and should make possible to compute efficiently correlators, form factors, and more involved observables like 3-point functions in n=4 super-Yang-Mills, which is also believed to be integrable. So that is our motivation to try to understand and develop the separation of variables methods. And so the question I will focus on is the measure in scalar products. So for GL2 type models, we can write this, the scalar product in these new separated variables as some integral over them, and then we have the two wave functions represented by Q functions. And then there is also some non-trivial object, this measure, in the integral. So when we do a change of variables to this nice basis, like always we get a Jacobian, which will appear in the integral. So like for hydrogen atom, this would be the spherical volume element. And for spin chains, this measure has been worked out. For instance, for the GL2 case, for many, many different models, and for instance, for spin chains, it takes some kind of product of van der Monde type determinants. So now for higher rank GLN models, the wave functions already are a bit more complicated, and it was also recently understood precisely how the wave functions become factorized. But the measure for higher rank was not known at all in the quantum case. It was never discussed in the literature. The only result was the classical limit, which should be the classical limit of the quantum speed chain derived by Smirnov and Zeitlin in 2002. So in this talk, I will describe our results where we were able to find this measure for any SUN or SLN spin chain at the quantum level. So first I will speak about the compact SUN spin chains, and then about the generalization to non-compact SLN case, even though that was the case we did chronologically the first. And then I will speak about some extensions to field theory very briefly in conclusion. So just very briefly, when the model I will discuss the most, the SUN spin chain and fundamental representation, where we have Cn space at each side. So the usual Hamiltonian, but what we also do is we add the generic inhomogeneities and the generic but diagonal twist matrix. So that is important for regularization purposes, although in some cases we can smoothly take the limit when we remove these deformations. So then of course, this is all based on the usual rational R matrix, and one can build the standard transfer matrix that gives commuting integrals of motion. So whose eigenstates form the basis of our space. And these eigenstates factorize in the special basis of separated variables labeled by X. So for spin chains, the idea is that this basis should be obtainable as eigenstates of a commuting family of operators B, which are polynomials, and these X's are just their roots, which commute with each other, can be all diagonalized at the same time. And for SU2, this B is just one of the elements of monodromy matrix. And the eigenstates are labeled by these eigenvalues determined by inhomogeneities, and all the combinations of plus and minus signs precisely give 2 to the L possible choices, and they label a complete basis of our spin chain space. So then for SUN, the picture is more complicated, and the B operator is now a rather non-trivial polynomial in elements of this monodromy matrix. So it was worked out by Sklyanin for SU3, then by Smirnov for general SLN, and in our paper we also wrote that it's in a slightly more explicit form. So let me briefly summarize the results, and then I will discuss them more pedagogically and with more details. So for SUN case, we started working on this problem in this paper from 2016. So first we understood that one needs a slight modification of Sklyanin's B operator, so by adding an extra similarity transformation to remove degeneracies, and we denoted the resulting objects as a good monodromy matrix and good B operator. So then the first result is that we found the spectrum of these X operators, so of the separated variables. So now we understood precisely how the wave functions factorize. And the second observation that we made is that one can use this B operator in order to build the eigenstates in a very compact way. So in fact, one can simply act on the reference state with these B operators evaluated at beta roots that can alternatively be described as roots of the Baxter polynomial, so fixed by the Baxter equation. And this gives the eigenstates for any SUN, as we observed. And so I would like to emphasize that in this picture there is no need at all for any nested beta ansatz or any recursive procedure. So it works in a very compact way. And one can, in fact, simply use the Baxter equation. Then we do not invoke the nested beta roots at all.
Is it complete? Is it the basis?
Yes, it turns out. So this was initially a proposal that we have proven in special cases, but we did not prove it in general. Later it was proven, and all these questions were answered positively. So it is complete, it gives a full basis, and it, so it's, now it is on the status of a theorem. So that is, I will briefly describe the history of this subject. So this second statement was proven for SU3 in the paper of Lyashik and Slavnov. So it was also shown there that it works not just for fundamental, but for any symmetric representation at least. And then for SUN, the full proof was found only 2 years after our paper by Paul Ryan and Dima Volin. And they also showed the equivalence of this approach with another way of constructing the X basis that was proposed by Jean-Michel and Giuliano. So again, after our paper, their paper came out in 2018 and then was continued by a series of others. And the idea there is that one can build the basis by acting on some reference state with T operators evaluated at some inhomogeneities, instead of diagonalizing the B operator, but it was proven that the two approaches precisely give the same basis. And so I will speak about this in more detail a bit later. And so that concludes the SUN, the description of factorized wave functions for SUN. And let me also mention that the analogous statement of this complex construction of eigenstates was also found for super spin chain SU1/2 in my paper with Nikolai. So again, we can build for SU1/2 an operator B of U, which generates eigenstates by simply acting BBB on the vacuum. But now this operator, we do not make any statement about separation of variables now. So this is just a statement how to build eigenstates. Hopefully it should be related.
Which type of representation?
Fundamental. Fundamental, yes. So now turning back to the question of the measure, what we can observe experimentally is that overlaps between these X basis states look rather complicated for SUN. And the hope would be to find a way around this and to try to still find some more simple expression for the measure. So this is what we did in these two papers last year. So first, the result is that we found a dual kind of operator. Instead of B, that's a C operator for SUN, which gives a separated variable basis, which factorizes the bra states, so the dual, the covector states. And the main observation is that the B and C eigenstates have simple overlaps, and it's precisely these overlaps which feature in the measure. So it's natural to pair them and describe the measure in this basis. So then we found also an alternative way to compute these overlaps, which precisely give the measure in separated variables. And it is based just on Baxter equations. It bypasses the operator construction. And in the end, the measure is found as a simple determinant of some nice integrals. So already very suggestive representation. So then after this, this year, another paper of Jean-Michel Giuliano and Vignoli appeared, who found an alternative, yet another description, presumably for the same measure. Now it is described in terms of some rather non-trivial recursion relations, which give a different point of view on the construction. So, and now as in terms of applications, as one of results, what we immediately get are simple determinant expressions for a large class of form factors that I will discuss more precisely soon. And so now knowing the measure, we have control over scalar products constructed from coefficients of these B and C operators, and also from conserved charges. And it is likely that this set of operators is complete, so we can write any operator in terms of them, and at least in principle, write the scalar product in this SOV basis for a generic operator. So for a generic operator insertion. Yes, and many of these statements can be generalized for SLN, so I mean for infinite dimensional representations for sites of the spin chain. All right, so now let me discuss all these results in a bit more pedagogical way. So what I will focus on in view of the very limited time, I will discuss the derivation of the measure in the most detail. So, and first for SUN spin chains. And let me start by SU2 spin chain, where the result, of course, was known for a long time, but we understood a very compact way to derive it from a slightly different approach, which is important for us because it generalizes almost immediately to any SU3. So the idea here is to any SUN. So the idea is the following. Since we know that eigenstates of the transfer matrix are orthogonal to each other, and they are represented by Q functions in separated variables, this orthogonality should imply some nice orthogonality properties for the Q functions themselves. So how could we try to decode it? The idea is to start from the Baxter equation, the usual Baxter equation for the spin chain. So this Q1 is just the polynomial encoding the beta roots, so also it has this twist. And so Q theta encodes the inhomogeneities of the spin chain, and Baxter equation has this simple form where plus and minus are just shifts by plus or minus I over 2. And tau 1 is the eigenvalue of the usual transfer matrix in fundamental representation, which encodes all integrals of motion. So now let's just, by dividing it with some overall factor, we can bring it to a slightly different form. So just this difference operator acting on the Q function gives 0. The operator is just this, so D is again simply the operator of shift. And then the main observation is the following, that this operator is self-adjoint with respect to a simple scalar product. And then, like in quantum mechanics, when we have the self-adjoint property, we can almost immediately deduce some kind of orthogonality. So more precisely, we introduce this scalar product, this bracket, as an integral over a large circle in the complex plane. In particular, the circle has should encompass all the poles of these Q theta plus minus factors, so goes around all the inhomogeneities and far away. And now, to prove this self-adjoint property, we just look. If we write it more explicitly, so we take two test functions, f and g, act on one of them, and then the observation is that if we do a change of variable in this integral, so shift the contour a little bit by plus or minus I, in order to transfer the shifts away from g and onto f, So then we observe that the expression for f is precisely the same Baxter operator acting now on f. So the reason for that is the nice form of these coefficients in the Baxter, which combine in precisely this way. So this, in this way, we prove this key self-adjointness property. And like I said, it allows us to quite easily derive orthogonality. So for another observation that we can introduce L such brackets, where L is the length of the spin chain, by just inserting exponential factors. Since they are I-periodic, they are like constants for the Baxter equation. And now, using this, so we label these brackets by J, and now we can consider, in order to derive orthogonality, we can consider this combination where we take two states, A and B, and now such a bracket would be zero. Because if we connect here in the first term with this operator to the right, and it annihilates the Q function. And in the second term, we can use the self-adjointness to act with the operator on the left, and it would annihilate that Q function. So the whole combination is zero. But, so now we can plug in these operators. The only difference between two states comes from the difference in transfer matrices, eigenvalues. And they contain these integrals of motion, which in the twisted situation uniquely identify the state. So we find a system of linear equations for these differences of integrals of motion. So multiplied by some coefficients, which are the integrals of such combinations. And since we are considering two different states, at least one of the differences has to vanish. So it means this homogeneous system of linear equations must have a non-trivial solution. In other words, its determinant has to be zero. So in the end, what we find is that determinant of these integrals has to vanish whenever we are considering two different states. So what it actually means is that this is precisely the property that characterizes the scalar product. So now the natural conclusion is that this should be the scalar product in separated variables, so where these Q functions represent the wave functions of the two states. And so let me also mention that now, so this integral goes around all these poles, which are here. So in the end, it is just a sum of residues at thetas plus minus I over 2, or in other words, and I said a bit earlier that these are precisely the eigen values of separated variables for SU2. So in the end, we precisely get a sum over Q functions evaluated at the separated variables, which is very nice. And one can easily show that this construction matches known results for the measure for SU2. So in this simple way, we reproduce the SU2 measure that was computed, of course, much before. And now we can, let me explain how this generalizes to SU3. So for SU3, the difference is we have two types of beta roots, momentum carrying and auxiliary. And main new feature is that we should use not only the momentum carrying Q functions, but also Q functions with two indices, or in the natural notation, they are Q functions with one upper index. So the different choices of them give different dual choices of beta roots, corresponding to dualities in beta ansatz. So now the argument is very similar. Now we have two Baxter equations. So one of them annihilates Q with upper index, another with lower index. And now we have two transfer matrices, tau1 and tau2, which are in fundamental and antisymmetric representation. And together they characterize the state uniquely. So what we observe now is that these operators are not self-adjoint. Instead, they are conjugate to each other. So if we flip the functions, we change one operator to the other one. But still, exactly the same argument as before goes through. When we consider this difference, it has to vanish. And so I will skip the details since they are very similar to SU2. So we arrive at this kind of equation. And now we have freedom, which of the three Q functions we choose here and which of the three we choose there. So with a particular nice choice, we get a linear system, a square linear system. We have two L variables, which are differences of integrals of motion. And we have the good number of combinations to give a well-defined set of linear equations, two L equations for two L variables. So in the end, again, determinant has to vanish, and we arrive at the scalar product, which has this nice determinant form. So one new feature compared to SU2 is that now we have two different Q functions appearing for one of the states. And another feature is that now they are not just, don't come just as Q, but they are shifted by plus or minus I over 2. And one can see again that each bracket is just a sum of residues. So we arrive at the formula for scalar product of this kind when we expand this whole thing. So we have some non-trivial coefficients, then Q's for one state evaluated at theta plus minus I over 2. And that matches the spectrum of Sklyanin's B operator. And then we have Q's for the other state, but they come in more non-trivial combination, in fact, a determinant, evaluated at some other arguments. And one can ask the question, could we build the basis where this second part also is precisely the wave function of the state, which we know is the case for the first part. So, and the answer is positive, so we can find an operator interpretation of the whole construction. So, the formula that I showed is just this scalar product of two wave functions with the measure, which we now know from the simple determinant representation. So, and this measure we find from explicit construction on the operator level. We can compute it from constructing explicitly these two separated variables bases. So this first factor is the usual scalar product, is the usual representation of one wave function, but the second one is the covector wave function, so we need a dual basis of these separated variables y. And the first basis are eigenstates of the familiar Sklyanin's B operator. But what we realized is the second basis also can be understood as eigenstates of a new operator. So it is in some sense dual to the original one, and in fact has very similar form, so in terms of minors of the monodromy matrix, but now the shifts are slightly different. So we can compute quite explicitly for some small length of the spin chain this matrix of overlaps between basis elements, and we observe that it precisely matches what we got from the Baxter equation. So as a result, the whole construction is put on a firm ground, and we find this nice expression for the measure. So I have to skip many details here because the proof of this, of how to build these bases is rather non-trivial. So let me give just a few details. So how can we actually construct these states? So after the works of Jean-Michel and Giuliano and the paper of Paul Ryan and Dima Volin, we understood how to build the X basis. It can be done by acting on the reference state with transfer matrices evaluated at some inhomogeneities. And we realized that a similar statement is true for the C operator. It is diagonalized, again, by acting with some slightly different transfer matrices on another reference state. So the proof of that is quite non-trivial, and it's generalization of the highly non-trivial methods developed by Ryan and Volin in this paper. So they are based on some non-trivial commutation relations between the B operator, involving the B operator, and on some representation theory insights where they were able to identify Gelfand-Zetlin patterns in order to label all the objects in a meaningful way. And these proofs go through in our case as well. So another comment is notice that for SU2 this overlaps matrix is diagonal, but for SU3 it is not, and nevertheless the elements are still simple. So that's one of our non-trivial observations. And so in the final result is this determined expression for the scalar product. So let me mention an alternative approach by Maillet, Nicolai, and Vignoli. So where they fix the measure indirectly by deriving a set of recursion relations for it, which presumably should give exactly the same measure. And it would be interesting to prove this more explicitly. So also they have another measure found in a basis where the wave functions look quite different from the original one. So as an application of our results, let me show just one of them. This is the computation of diagonal form factors, where we take diagonal form factor of derivative of an integral of motion with respect to some parameter, such as the twist or the inhomogeneity. So these are already quite non-trivial objects, but using again the self-adjoint property, they can be computed in a very simple way, as we understood. And so I will not go into details here, but we again find determined representations for them in terms of similar integrals, and in the denominator we have the norm that I showed before, which is also nice. So, and all of these observations generalize to SUN as well. So let me just mention that such tricks with Baxter equations were used first for n equal 4 super-Young meals in a particular setting in my paper with Andrea Cavalli and Kolya Gromov. So then we generalized it to apply them for SLN spin chain, and then only then we did the compact SUN spin chain case. So a few words about how it works for non-compact spin chains now, when we have infinite dimensional highest weight representation of SLN on each side. So now we actually have integrals instead of sum. The separated variables in some sense take continuous values. And to ensure the convergence of integrals, we insert some aperiodic measure which decays at infinity. But then so and again we have some Baxter equations for SL3 which work exactly the same way like before. So we would like to have this property of one operator adjoint to another, but in fact we don't have it precisely, because the price to pay for this decay of the measure is the presence of poles when denominator vanishes. So they go along some vertical line. And when we shift the contour to prove this property, we cross the poles. So in principle, the construction could fail at this point. But very remarkably, we observe that all these poles cancel when we specialize to one of these functions being a Q function, which is the case we need. So the cancellation happens due to non-trivial relations between T and Q functions, and it ensures that the whole construction works like before. So the cancellation is quite non-trivial, and we view it as another indication of that our approach reveals some natural structure in the spin chain. So for SLN, the structure of the measure is the state-independent operator. Like I said, it involves the shifts. So it has this nice form of kind of tensor product of two determinants. And what's remarkable is very similar to the conjecture of Smirnov and Zeitlin based on semi-classics. So at least structurally, it reproduces their conjecture, which was derived from semi-classical observations and direct quantization of the spectral curve. So we match their semi-classical result. So in an upcoming paper, we also generalize to any spin S of the representation. So what I said was for spin minus 1/2. So then for any S, the measure becomes more complicated. It involves these gamma functions. And we reproduce the results derived by Derkachov, Monashov, Karchemsky in a completely different way. So now to build the SOV basis, we can use the same strategy, but now we act with more involved T functions in non-rectangular representations. So when we close using the technology developed again by Ryan and Volin in a later paper, and now the integral can be closed in the lower half plane and becomes a sum over discrete set of poles which precisely match this basis, and we can check that the measure of the overlaps of these basis elements reproduce what we got from Baxter equation. So now they form some infinite matrix. We can check that the matching is perfect. So very briefly, in the remaining 1 minute, I will say about extensions to field theory, such as integrable super-Young-Mills theory. So there, the single trace operators built out of various fields map to eigenstates of some integrable spin chain at weak coupling. So at finite coupling, we expect they should be a product of some Q functions, which are known at any coupling from quantum spectral curve equations, set of functional equations for exact spectrum, has found many applications. So recently with Michelangelo, we applied it to some non-supersymmetric case, so they work very well. And the hope is to link this with exact 3-point functions, which are much less understood than the spectrum. So to reconstruct them from some scalar products of wave functions in separated variables. And we found in 2018 the first example where actually this can be done for a very particular correlator involving some non-local Wilson lines, but it takes extremely simple form. It's just a scalar product of 3 Q functions to all loops in the coupling. And similar structures were seen in very different regime by localization. So this gives a hope that there should exist some hidden structure behind correlators. And we are exploring some more extensions to another integrable model, which is just two scalar fields with quartic potential, known as fishnet CFT. So it's also believed to be integrable, although it has no supersymmetry. And there we find very similar structures for some correlators. So this derivative in the coupling is very similar to form factors that I showed before. Again, it's a correlator of two operators with Lagrangian, but given by very similar structures. So and there are many, many future directions. So in view of time, let me just leave here a summary and some directions for the future. The main one, which we are exploring now, is to find new structures for correlators in ADS-CFT that hopefully could allow us to finally solve an equal force Superior Mills completely. Thank you very much.
For what I can understand, you don't compute directly, let's say, the measure. You don't compute directly the scalar product between left and right SOB basis. But you deduce that what you get is the scalar product of, let's say, eigenstate of the transfer matrix. Can you go back to the slide for the case SL3?
Yes. So here, for instance, well, this one.
Yes.
Yeah, so what happens is that first we find the measure with respect to which wave functions are orthogonal, and it's natural to expect that this should be the measure in the appropriately chosen basis. But so at this point we don't say anything about basis. But
you use after the...
yes, but then we also understood that in fact there does exist a basis where precisely this measure is the matrix of overlaps of basis elements. So with this construction, the measure we first derived from the Baxter equation, then we verify that it precisely matches what we get from operator construction.
Yes, with the construction of X and Y,
yes.
With the transfer matrix, probably you give in the next...
Yeah, with transfer matrix is one way. Another way is to directly diagonalize B or C operator.
So what you are showing is that the representation that you get correspond to wave function associated to this basis X and Y.
Yes, and also that the overlaps match, which we checked explicitly in some cases.
I'm just questioning if you have proof that what you are computing is really the scalar product between the state CA and CB.
Right, so the statement to prove would be that this overlap of X and Y indeed matches the coefficients we get from expanding these integrals. That's the statement you would like to, this is the statement you are asking about, right? So when...
Look at the direct calculation of this X times Y.
Right.
How do you say that this is really the scalar product?
Yeah, so this is what, yes. So we know that the wave functions have the form predicted by our integral. This can be proven. So what remains to show is that measure also has the form predicted by integral. This we so far checked only for some explicit cases, like Spinchains of some fixed length. So it would be interesting to prove it in full generality. But there is virtually no doubt that it should be the case. We have some indirect argument under some assumptions which guarantees that this measure should match, because it's a kind of argument, since we know the wave functions are represented like that, there is essentially, and we know the Q functions are orthogonal with respect to known measure, there can essentially be only one kind of orthogonality between two complete bases. And so since we know the Q functions are orthogonal, it means this matrix has to match what we had. But it relies on some assumptions. So for instance, the assumption that overlaps between psi A and psi A, which are the norm, that these overlaps are non-vanishing. It would be interesting to clarify this a bit more.
I have a question regarding the interdimensional case. So there you advocated that now the integration should run over R, but there are only cases where integrations in scalar products in the separated basis
also run where, sorry?
Over other sets than R. So if you take SL2C, which was done by the
Yes.
and others, then the separated variables are parameterized by the X product n times R.
Yes, yes, yes. So this case, what I'm speaking about, this is for representation of spin minus 1/2 of SLN.
Yeah, but how really you would fix the integration domain?
So this is a matter of making the correct guess. For instance, here we observe that precisely with respect to this measure, our two operators become conjugate to each other. So it's the natural guess for the measure. Alternatively, one can build the basis of separated variables explicitly. So now it is some discrete set of basis and of basis elements. But then we find that precisely this integral over R becomes the sum over these basis elements once we close it in lower half plane so that it is a sum over poles. For SL2C, which you spoke about, the situation would be quite different. Probably would be very interesting to decode it and to generalize to SLNC. And that's also an important problem in relation to this fishnet model that I spoke before, where actually we need even more involved thing. We need the principal series representations there.
Give some formula for the orthogonality method.
You mean this thing?
No, for L of x, y is just the scalar product of x and
Yes. Mm-hmm.
Is there some close, like, double product or something like this?
So directly for x and y, we did not look for a closed formula. So if you want to actually extract not the scalar product itself, but one element of the matrix, so what we do is we just take this determinant, pick the corresponding piece of the wave function, and collect the coefficient. Perhaps there exists a nice formula directly for mxy. So what Maillet and Nicoli found is a set of recursion relations for these quantities, which look rather non-trivial. Perhaps they could have some simple solution. Who knows?
Just to understand what characterizes the states CK and CB regarding to what's the solution of the equation in
Yeah, I mean that psi A and psi B are left and right eigenstates of the transfer matrices.
Okay. So where you fix the states, how you fix the states when you make the calculation?
They are characterized by Q functions. So in this in the twisted situation, for instance, this momentum carrying Q function identifies the state uniquely.
And what are the equations that characterize your Q function?
It's the Baxter equations. The usual. Well, maybe I did not go over this in much detail. We just have the usual Baxter equations for SU3 spin chain. It's a third order difference equation. So its coefficients are the transfer matrices, which are some degree L polynomials. So if you impose that this equation has 3 polynomial solutions, it uniquely fixes both the solutions and the transfer matrices.